Our next problem is a variant of the previous scheduling problem. And so remember, in the previous scheduling problem, what we saw that we have a set of jobs, a set of intervals that had to be scheduled on a single resource. Right? The single resource could not schedule more than one set of jobs at the same time. So we had to select a subset of non-overlapping jobs, which was the largest size. Okay. In this next version of the problem, what we have is that we again have a set of jobs. Okay, so we have a set of intervals, each having a start and a given finish time. But now we have more than one resource on which we can schedule the jobs. Okay, so if you think of your resource as a CPU, you might have more than one CPUs on which you can execute your tasks. Okay, or maybe if we come back to that example of having a classroom or a cinema hall, I think what we mentioned, now you have more than one halls, you have more than one rooms where you can screen your movies, right? So now the problem is that since we have more than one a resource, well, in this setting, we'll assume that we have as many number of resources as we want. We will want to satisfy all the jobs. Okay, so we don't want to leave any person disappointed. So all the jobs, all the intervals that want access to the resource will be satisfied. Okay, so what are we trying to achieve then? Right? We are trying to optimize the number of resources that we utilize for this purpose. Okay, so if you come back to that classroom, if you think about the classroom analogy, we have, we want to, or the movie hall application, we want to use as few number of halls to satisfy all the possible requests. Okay, so I hope you see how this problem is different from the previous problem. So for example, if we had just two jobs of this nature, these are non-overlapping. So we can have, we can just schedule them in a single, in just using one resource. If we had something like this, right, we had these two. So not considering the previous two ones, we're just looking at these two requests. Here it is clear that at this point in time, these two jobs overlap, so they cannot both be scheduled on the same resource. So we'll need two resources to schedule them. Okay. If we look at maybe some other example like this, let's say we have these three resources, these three intervals. Let me just label them A, B, and C. What you will notice that these can be scheduled in this way, right? The first A and C, these two don't overlap. So these can be scheduled on one resource, and the job B can be scheduled on the other resource. So again, we can just do with two resources. Okay, so we'll talk about partitioning the set of intervals into groups, right? So here in the first case, we just have one group. Here we have two groups and so on, right? Within each group, so this would form a group, for example, here. Within each groups, the intervals have to be non-overlapping. Okay, so this would be the second group here. Here it just has one interval, but the idea is all the intervals within a group are scheduled on a single resource. right? So they have to be non-overlapping. And we want to partition this input into different such groups. And since we want to minimize the number of resources, it's equivalent to saying we want to minimize the number of groups that are formed. Okay. So our input to the problem is a set of n intervals. Each of the interval has a given start time and a finish time, okay? Just like in the previous problem. Now the output that we are looking is to partition. So we want a partitioning of the input intervals into a minimum number of groups, such that each group contains only non-overlapping intervals. Okay, so this problem description is a bit informal. Okay. You're not formally defined what a overlapping is, and so non-overlapping. Okay, but I think it will suffice for this purpose. That right. So we want to partition. We want to divide the set of intervals into a minimum number of groups. Right? And within each group, it should be the case that no two intervals overlap, just like in the previous problem. Right? The intervals within each group have to be non-overlapping, non-conflicting, because they are all scheduled on the same single resource. Okay, so if we divide the input into k groups, we'll be using k resources to schedule the jobs. Okay, so this is the problem that we would like to solve. So how could we approach this problem? Could we try something like in the previous problem, like try a greedy approach, something like in the previous problem? So maybe, so we would consider intervals one by one and do something with them, right? So in this case, maybe we could consider intervals one by one and decide which group to put them in, right? So how do we form these groups? Right? Initially, how many groups are there and how do we go about this? Okay, so, and how do we consider the input, right? If you're considering the input one by one, shall we order them in increasing finish times like we did in the previous problem? Or maybe shall we order them by increasing start times? Or maybe something else, maybe increasing size of the intervals, or I don't know. Okay, there are varying number of possible orderings, right? So which one could be considered? Okay, and one kind of natural thing to think about is when we consider the next interval, we'll try and put it in the first group, right? So let's say we have some, at any point, we consider the first interval, okay, and this, we have not yet formed any groups. Initially, there are no groups, let's say, and we consider the first interval and put it in group one. Okay, and then we consider the next interval and try and put the next interval in group one again. Okay, but if it conflicts, if there's an overlap with the interval in group one, we'll create a new group and put it in the next group, group two. Okay, so then we consider the third interval. Okay, and when we consider the third interval, we'll try and again put it in the first group, group one. If there's an overlap, then we'll try and put it in the next group, group two. Okay, and we'll check for an overlap in group two also. If there's no overlap, great, it can go into group two. But if there is an overlap, we'll create a new group, group three, to put that interval in. Okay, and so on and on. Okay, so recursively, iteratively, we pick the next interval that we're considering, and we try and fit it in one of the existing groups. Starting from group 1, we'll check, then we'll check group 2, and so on until all the number of groups we have. And if it overlaps with an interval in all the groups, then we'll end up creating a new group for that interval. Okay, so this is the idea that we're looking for this algorithm. But the question is, in what order do we consider the intervals? Okay, what is the sorted order? Okay, so in this case, it turns out that the method that works is to consider the intervals by increasing start times. Okay, so the algorithm is basically what we just described. So I'll maybe write it down clearly. So the algorithm for this problem that we described is, so sort the intervals in order of their, in increasing order of their start times. Okay. And now we consider the intervals one by one in this sorted order. Okay. So for each interval in this sorted order, for each interval, let's give it some name. For each interval, let's say I. And what we'll do is, we basically said we'll put it in the first possible group. By this we mean, so that is, it's the first group whose intervals don't overlap with I. Okay, so so we start with group 1, try to put I in it. If not, if there is a overlap, it's next consider group 2, group 3, and so on in that order. Okay? We don't start by checking with some random group. Okay, so that's the idea. We are systematically considering the groups from group 1, group 2, and the first possible group that it can fit in, where there is no overlap, we put the interval I in it. Okay. Now, of course, it can be the case that I cannot be put into any of the existing groups, okay, because it overlaps with some interval in all the existing groups. Okay, so if I cannot be put into any of these already existing groups, then we said we'll create a new group. Okay, create a new group and put I into it, right? Okay, and we iteratively do this for each interval. Okay, so this is it. This is our algorithm. Okay, and as in the previous case, I guess, well, I hope you're not really convinced that it is correct, right? That it will actually give you the right output. Okay, so we want that the number of groups created is the least. So why is it the case by doing it in the way that this algorithm is doing, right? That is by sorting the intervals and increasing start times, right? And then doing this process. Why is it that it will always guarantee that the output, that is the number of groups it creates, is the least? Okay, so I hope it's not obvious. It is not obvious, and it is an intuitive way of doing it. Okay, so I hope you see that also. This algorithm is rather straightforward. Right? It's not complicated. It is intuitive, but well, in this case, it turns out to be correct. And but how do we actually argue that it's correct? So the correctness proof for this algorithm also luckily turns out to be not too complicated. So we want to show that the partitioning, right, the number of groups created by this greedy algorithm is an optimal number of groups. Right? Clearly, within each group, clearly the algorithm is not putting overlapping intervals. Right? Only when an interval does not overlap with all the other existing intervals in a group will it be added to a group. Okay, so that part is fine. The algorithm is going to definitely output groups of non-overlapping intervals. Okay, that cannot go wrong, but we need to argue that the number of groups created is the least. Okay, so let's say supposing our greedy algorithm partitions the input into some k number of groups. Okay, so what we need to show, we need to argue that any other partitioning of the input intervals will require at least k groups. Okay, you cannot do better than this. There can be no partitioning of the input intervals which would take, let's say, k minus 1 groups or lesser. Right? So any other partitioning will either take k groups or more. Okay, in which case our greedy algorithm would be optimal also. Okay, so that's what we need to argue. Okay, so at least k groups are needed by any other partition. Okay, so you need to understand that in general, for a given problem, you might have multiple optimal solutions. Right? There may be different ways of picking the optimal solution. Right? Like we have seen, like for minimum spanning trees, for example, you could have different minimal spanning trees that have the same weight. Okay. In the previous problem, we could have different set of non-overlapping intervals such that the set size of the set was the same. Okay. Over here again, we might have different ways of partitioning the input into groups in which the number of groups created is the same. Right? What we need to show is this greedy algorithm is doing one thing, right? It is doing something and it's producing one output. What we need to argue is this output is one of the optimal solutions, right? There may be others, but it's definitely as good as any other. Right? That's what we are trying to argue. Okay, so that's why it requires at least any other partitioning will require at least k groups. Okay, if it's another optimal partitioning, it will take exactly k groups, but it can't take lesser than k groups. Can't do better than our greedy algorithm. Okay, that's what we want to argue. Okay, so right. So again. Okay, so the trick to argue this is you consider the point at which the group K was created, right? So consider the first interval in your input, right? When you're considering the input in the order of increasing start times, consider the first interval that caused the group K to be created. Okay, so you had these groups 1, 2 up till k minus 1. Okay, and in group 1 maybe you had some intervals, right? In group 2 you had again some intervals, okay, and so on. Okay. Group k minus 1 had some intervals. Okay, and now when we try to add this at the point at which this group K was first created, okay, what happened at that point? At that point, I took the interval that I considered, I tried to first put it in group 1, but there was an overlap. Okay, I tried to put it in group 2, there was an overlap, and group 3 and so on up till group k minus 1, there was an overlap. Okay, so maybe our interval, well, okay, so we are considering intervals with increasing start time. So maybe our interval that caused the creation of group K, maybe it is something like this, right? So what has happened is that since it is in conflict with all the other groups, intervals in all the other groups, the moment that this interval starts, so let's say it has some start time S, this time instant, right? If I draw this line here of this time instant S, the start time of this interval, clearly at this time, there has to be some interval in the other groups that is running at this time, right? Because I tried to put this interval, okay, I tried to put this, let's give it some name, this interval I, right, that caused the creation of the kth group. I tried to put this interval I in, well, in the first group. Initially, I tried to put it in this group, but there was an overlap. So that means that the start time of this interval fell before the finish time of the interval that was already in group 1. Okay, so it overlaps. Okay, and the same thing for the other groups, right? In group 2 also, the start time S would have to be before the finish time of the last interval. Okay, that's why there was an overlap. Okay, and so on and on. Okay, so this is the scenario, right? So you have at time instant S, you have 1, 2, for each group, you have one interval with which this interval I overlaps. Okay, so what do you notice? Right? So you notice that at time interval S, they have to be exactly, well, they have to be K intervals that need to be running simultaneously at time S. So if you think of them as jobs, at the time S, you have to have K jobs that have to be running at the same time. Okay? There are K overlapping intervals, right, at this time. Okay, so there is no way that you can do less than K, right? If you have at time instant S, if you have these K intervals that overlap, there's no way you can schedule them all with less than K resources. Okay, so you have to have these K groups. Okay, and that is why any other partitioning of the input intervals will require at least K groups. Okay, it can use more, of course, but it will require at least K groups. And K was the value which was given by our greedy algorithm. And so what we have actually produced is indeed optimal. Okay, so that's the argument of the correctness for this algorithm.